Welcome back, guys. This is part 12 of our 8086 programming tutorial. In this part of the video, we're going to write a program that displays the content of a 16-bit register in the decimal format on the screen. What I mean is, say for example, AX contains 61H. In that case, we want to see 97 as an output, not the character A on the screen. Let's see here, if AX is 61H, then if we print it, we should be seeing 97, not the character A on the screen. See, if we want to see character A on the screen, then we can fall down to our typical approach. What is that? First, we can store this 61 to DL register and then 2 to AH register, and then int 21H will display the equivalent ASCII character of 61H on the screen, which is A. But that is not something that we want here, right? What we want is, if it is 61H, that is 97 in AX, then in the output screen we want to see 97. You got the difference? Yeah, that is what we want to achieve. And the second thing is, we'll be assuming, okay, the numbers are unsigned and integers for simplicity. Okay, let me now explain you briefly the approach that we're going to take to solve this problem. There are a few things I have to tell you. Let me tell you one by one. We'll be starting with what we know. What we know? We know we know how to display a character on the screen, isn't it? Say, for example, we want to display the character A on the screen. What will you do? You will be storing that character. You will be actually storing the ASCII value of that particular character in DL register, and then you will be, I'm just keeping it blank for the time being, whatever the ASCII value of that character, you will be storing it here, and then you will be storing 02 to AH register, and then you'll be calling this, or you'll be executing this int21H instruction, which will call the appropriate interrupt service routine to display the content of DL register as a character or as a ASCII code on the screen. So here the point of interest is then knowing the ASCII code of a particular character. Yeah, certainly you can store the character as it is here in this way. So that way automatically the assembler will copy the right ASCII value of that particular character that you mentioned in the instruction to the register. But suppose that is something that we do not want. Suppose we want to write here a number and we want to display the corresponding ASCII code on the screen. Suppose we do not want to write here directly the character. Okay, although we can write. Now, in that case, if we do not want to write the character directly here, what we can do is we have to write here the ASCII code of that particular character. Now, the question is, how do you know the ASCII code of these different characters? Yeah, one thing is that, yeah, you have to remember. At least for a few characters, it is good that you remember. Otherwise, certainly you will find it in public space. I mean, over the internet. You just have to do a Google search. I'll be coming to that point in a moment. But see, suppose if you know the ASCII code of a few characters, then from there you can actually, you can actually derive the ASCII code of some other characters also. So, for example, if you know the ASCII code of the uppercase letter A is 60, what is that, 65, then you know immediately what is the ASCII code for the uppercase letter B, which will be 66. Then for C, it will be 67. I mean, 65 plus 2 is 67. A plus 2 is sort of C, right? That is, C is 2 characters away from A. 67 is 2 integers away from 65. Sort of that. So similarly, you can derive actually what will be the ASCII code of uppercase Z. In that case, it will be 65 plus 25. Because you see, B minus A is 1, so 65 plus 1. Similarly, Z minus A is Z is 25 characters away from A, so 65 plus 25. Similarly, if you know the ASCII code of lowercase a, which is 97, immediately you know the ASCII code of all these 26 different characters like A, B, C, D, E, F, like that. So similarly, the lowercase z will be 97 plus 25, isn't it? So similarly, if you know what is the ASCII code of these digit 0, now see digit 0 is different from its ASCII code. Digit 0 is this, and ASCII code of digit 0 is, the character that represents digit 0 is 48 in decimal. So similarly, if you know for 0 what is the ASCII code, you will be knowing what is the ASCII code for the character that represents digit 1. That is actually 49. Like that, you'll be knowing what is the digit for, or what is the ASCII code of the character that represents digit 9. It is 48 plus 9. You see, there is this pattern. 48 you can write as 48 plus 0. 49 you can write as 48 plus 1. So similarly, 48 this 9 you can write as 48 plus 9. So if you want to know what is the equivalent ASCII code of, so our question is this. If you want to know what is the ASCII code, ASCII of the digit 9, it means the symbol or the character 9 here, this, then how you can do that? You can actually write 48 plus the number 9 here. This is your number. If you add this thing, whatever the value you get, so it will be 48 plus 9 is 57. So this 57 will be the ASCII code for this digit 9. That is, if you store 57 here, if you store 57 here, and if you print it, you'll be seeing on the screen the digit 9. Okay, so see the pattern here. Whatever the digit for which you want to see, whatever the digit for which you want to know the ASCII code, you just have to add the the corresponding number. In the sense, if digit 9 means the number 9, digit 1 means the number 1, like that, with 48. Immediately you'll know whatever the result is, that is the ASCII code for the character corresponding to that particular digit. I guess you got the idea, right? And again, let's come back to the point. If you forget these ASCII values, then certainly you can go to the internet and you can check. Say, for example, here, I already have checked actually. So you can write in Google ASCII code, just do a search. Whatever the links are shown, you just can follow any one of the link. I click here on this link, and or maybe this link will also work fine. And it will show you the ASCII table actually. Say, for example, I said here, you see, this is 65 is uppercase. This is the decimal equivalent, decimal number. The ASCII code for the character A is 65. So similarly, B is 65 plus 1, that is 66, like that. For lowercase a, it is 97, and all the other symbols. I mean, all the for all the other alphabets, you can see it here. 97 plus 25 is 122. And see the digits here. You see this digit 0. The ASCII code of 0 digit is 48. 1 is 49. For the character 2, not not the number 2. Okay, the character 2 ASCII code is 50, which is nothing but 48 plus the number 2. So for any digit, if you want the ASCII code, then you just have to add 48 with the number which is same as that particular digit, and then whatever it is, that will be the ASCII code of that particular character. Got it? Things are simple. I mean, you just have to give it, you just have to think for 1 or 2 minutes, you will get the idea, if it is still not very clear. But again, I hope it is done. Then what we have to do is, so we know how to display a character on the screen. So now our question was how to display the number. Say, for example, it is now 1, 2, 3, 4. We have to display this number actually on the screen. But what we know is, only we know how to display a single character. Okay, so how we can solve this problem? If we know how to split these digits from this number, then we can take this approach, because once we have the digit, we can compute the ASCII code by adding 48 to it. And once we have the ASCII code, writing these 3 lines, we can display the digit on the screen. So our question is now then, how do we split the digits from the number? I mean, how do we take away those digits? How do we separate those digits from the number? right? So to do that thing, let me explain you with reference to two high-level operators. Those are this integer division and modulus operation. What does this integer division do? Okay, let me give you an example. So for example, you have a number, say 7, simple number, 7 divided by 2. Now 7 divided by 2, if you perform integer division, say in C language, what this 7 by 2 operation is going to give you? It is going to give you the maximum number of times by which you can divide the dividend by wholly, you can divide the dividend wholly by this divisor. Here it is 3. So 3 is the maximum number of times, the whole number that you can divide 7 by 2. Right? So this integer division is going to give you this number here. And that technically this number is called as the quotient of that division operation. Quotient. Quotient of this division operation. The two parts actually in division, right? I mean, see, this quotient doesn't entirely cover the and this dividend actually. 7 by 2, all the result is 3, okay, but still there is something left. This leftover part, if you want to know, then you have to perform this modulus operation. 7 mod 2, it will give you the remainder, the leftover part. Technically, that term is called as the remainder. And what is 7 mod 2? 7 mod 2 is your 1. So this is technically called as the remainder. Okay, and like say this 7, technically the number which you are dividing, this is called as dividend, and this number by which you are dividing, this is called as divisor, and it produces two results. One is this quotient and one is this remainder. Isn't it? Now see, there is certainly a relationship. Let me tell you this thing for complete. I mean, you should think it and you should realize that that is true. What is that thing is, see, dividend, from this equation you can write dividend is equal to Q multiplied by divisor plus R. So for example here, 7 is the dividend. So 7 is nothing but Q. Q is 3, divisor is 2, plus remainder is 1. 3 into 2 plus 1 is your 7. Right? So now that's what we are going to use. Now we are going to make use of these two different, we are going to make use of this division actually, and we are going to make use of this concept of quotient and remainder. In C programming language, you have two different operators to achieve the thing. Now let's continue how we can actually achieve this thing, how we can make use of these two operators to separate the digits. See here, see if we divide a number by 10, let's say for example the number is, say, n is equal to 1, 2, 3, 4. If we divide this number 1, 2, 3, 4 by 10, integer division, what result we get? We get 123. And if we perform remainder or modulus operation on this number 1, 2, 3, 4 by 10, what result we get? We get this number 4. Another example you consider, say for example 567 divided by 10, integer division, what result you get? You get 56. And if you take the modulus 567 mod 10, you are going to get the result as 7. Now see, from here what you can see is that if you divide the number by 10, and if you take now this, as you know, this is the quotient and this is the remainder of the division operation. If you divide a number by 10, you consider the quotient, then what you're going to get? You're going to get all the digits except the last digit. Isn't it? It means the division sort of splits the original number, into two parts. One is the like division means division by 10 splits the original number in two parts. One part is all the digits except the last digit, and the other part is the last digit. And all the digits except the last digit is, you are going to get it in Q, and all the digits, only the last digit you're going to get in R, or as R. in both these examples, from both these examples, things, it should be clear to you, right? So 567 divided by 10, and this is true only when you are dividing the number by 10, certainly, right? So 567 divided by 10, it will split the number sort of in two parts. One is the number that contains all the digits except the last number, except the last digit, which is 56, and which is that is actually called as the quotient part, and the remainder part will be the digit, the last digit. Okay, that is, it will get away, it will strip away, or it will remove all the first digits, and it will keep only the last digit. You can think it that way. So now, as soon as I show you this thing, then immediately you know like how we can make use of this these two operation, or these two operator, to actually like get the digits one at a time. How you can do this? You just have to perform this operation repeatedly until and unless your quotient becomes 0. How? Okay, let me show you this example. Say, for example, n is equal to 1, 2, 3, 4. First thing is, you perform, say, 1, 2, 3, 4. If at this point, if you perform 1, 2, 3, 4 mod 10, what you're going to get? You're going to get this last digit out 4 in the remainder part. Isn't it? Okay. Okay, and after this, once we have this last digit out from this number n, we do not need this last digit actually, and we can get rid of this last digit just by writing n equal to n divided by 10. So in this case, it will be 1 2 3 4 divided by 10 will be stored back in n. That is, 1 2 3 4 by 10 is actually what? 123. That will be stored back in n. So what we do is, we first, on the number, we perform this modulus, we get the last digit, and after that we want to get rid of the last digit by writing the statement n equal to n by 10. So that way the last digit will be go away from the number. Done. Once it is done, if it is not 0, if the number is not yet 0, then we can repeat the same process again. That is what will be now, this is 123 mod 10. Whatever it is the remainder, that will be our that will be our the digit of interest. And then once we have the last digit out, we do not need it anymore, so we can write n is equal to n by 10. In this case, n is equal to 123 by 10, so that is 112, and this 12 will be stored back in it. So that way, the next time again, since it is not 0, again we can write 12 mod 10 to get the last digit, which is 2, and then we do not need this 2 anymore, so we can write n is equal to n by 10. This time it is n is equal to 12 divided by 10, which will be 1, yes, and that 1 will be stored in n. Still this 1 is not equal to 0, so we can write 1 mod 10. That will give us what is 1 mod 10? Remainder is 1, so this is our digit of interest, and after that we do not need this 1 anymore, so we can write n is equal to n by 10 one more time. This time it will be n equal to 1 divided by 10. And what is n divided 1 divided by 10? The quotient will be 0. That is, 0 is the maximum number of times wholly you can divide 1 by 10. 0 means 0. I mean, that's 0. You cannot divide 1 wholly by 10, not even once. So that 0 you have to store in n. So that way, now once this n becomes 0, it means we know sort of that our process is done. So that way you can see in each iteration we got our digits separated. 4 first, then 3, then 2, then 1. Now in this approach, although we got our digits separated somehow, you see here these digits are separated in reverse order. Our number was 1 2 3 4. But we got the last digit first, and then the second last digit, then the second to second last digit, then the second to second, then the first or the last digit. You got the point? So this approach is going to split or going to extract the digits from the number in a reverse order sort of. But then also for our task, it is okay. I mean, if we can split them first, then certainly we can write some extra logic or extra lines of a few lines of code to actually to reverse the order. There are different ways of doing it. I'll be showing you one simple way here, and that way will be first we'll be constructing a string sort of, and then we'll be reversing the string. But again, there are some other ways also. Those maybe I'll be addressing in the coming videos. But for the time being, let's first get the idea how we can implement this logic. That part I'll be concentrating. So here we know sort of, right? If we know here like how to separate the digit, then displaying the digit is not a problem because we already have seen it, like how we can do that, right? Displaying any character on the screen is not a problem. Suppose we have to display a digit, means first we'll be adding 48 to it, we'll be getting the ASCII code, we'll be storing it in DL, and then we'll be displaying it. So that way the digit can be displayed on the screen without any problem. So if both these two things can be done, now the question is that, okay, here I have explained the concept in terms of high level operators like integer division and modulus operation. But what if we have to do it in 8086 instruction? Which instruction is going to be used? Are there two instructions or one instructions? Yeah, those questions will be answered just now. See, the instruction that we're going to use is this div instruction. And there is only one. I mean, both these integer division and remainder, the results you can find both these two values q and r, you can find just by writing this div instruction. Only one div instruction. Okay, and the syntax of writing this div instruction is div and then divisor. That's all. It means what you see here, this div instruction requires only to specify the divisor. Then how come it knows what is the dividend? Okay, dividend divisor means, see here, this dividend, the number which you are dividing, it is called as dividend, and by which you are dividing, it will be called as divisor. And this operation will result in, it will give you two outputs actually. One is the q, one is the r. Q means quotient and r means the remainder. Okay, now div instruction, in div instruction you are going to specify the divisor. I mean, this divisor, whatever it is, you will be writing in div instruction. Then from where this dividend is going to come? Yeah, in 8086 microprocessor, this I mean 8086 instruction, when the 8086 microprocessor is executing this div instruction, it will always assume that the dividend is there in some predefined register. I didn't say any specific name of register because, see here, this dividend and divisor, these combinations, they could be of different types based on their size actually. Okay, let me write it here. They could be of 16-bit by, okay, let me start with 8. They could be of 8-bit by 8-bit division. Okay, now if it is 8-bit by 8-bit, then divisor certainly you have to specify here. Okay, but okay, let me write it in the form of a table. It will be more clear, I guess. So I'll be writing here what is the size of the dividend, and I'll be writing what is the size of the divisor, and then the default location of this dividend. Okay, and divisor you have to specify. So divisor, it will not be there in any default location. You can directly either specify it, or you can store it in a register, or you can specify the right name of the register here. But for this dividend, certainly there is a default location is there, and the location for, once this div instruction is over, that key will be there in some predefined register, and R will be there in some predefined register. That's I'm mentioning as location of Q, location of R in this table. Now let's fill this table. What are the different sizes possible? This dividend could be of 8-bit, that is you can perform 8-bit by 8-bit operation. So dividend is 8-bit, divisor is 8-bit. In that case, location of the dividend is AL register, location of Q is AL register, location of R is AH register. It means what? If you are performing a 8-bit by 8-bit operation, then this div instruction will take whatever it is there in AL as dividend. It means it will say, for example, you have in AL you have say 5, and in CL you have say 3. So if you perform div CL, what it will do is it is going to perform AL by CL. And whatever the result, the quotient of this AL by CL, the quotient is going to be stored in AL register, and the remainder is going to be stored in AH register. That's what I mean here. Okay, AL and H register. But again, another type of division that is possible is say 16-bit by 8-bit. That is, dividend is of 16 bits in size and divisor is of 8 bits in size. In that case, to store 16-bit, you need a 16-bit register, and the default location will be AX register. In that case, it means division will take this dividend, like from the AX register. Whatever it is, the content of AX, will consider that thing as dividend, and then it will divide whatever the divisor is specified in the instruction. And the quotient will go to AX register, remainder will go to remainder will go to DX register. Oops. DX register. Okay. Similarly, it could be of 16-bit by 16-bit also. In that case, dividend is 16-bit in size, divisor is also 16-bit in size, location is AX register, default location of the dividend, and the result, the Q part will go to AX register, the R part will go to the X register. And another one is possible, say 32 bits by 16 bits. Dividend size is 32 bits, divisor size is 16 bits. The location of the dividend, now say 32 bits you cannot store in a single register, so certainly you need to have two 16-bit registers, and those two 16-bit registers will be the combination of AX and DX register. Combinedly, they will be considered as the dividend, and then the location of the Q will be again AX register and R will be in DX register. Now when you write it in this way, it means this AX actually it is the it is the least significant word, and DX will contain the most significant word. The upper 2 bytes will be stored in DX, lower 2 bytes of this 32-bit number will be stored in AX register. And the whatever the quotient is, it will be stored in AX. Whatever the remainder is, it will be stored in DX. Now see, always the quotient might not fit in a 16-bit register. I mean, it might be more than, it might need more than, 16 bits. In that case, it will generate an interrupt, actually, division interrupt, division error interrupt. So you have to handle that interrupt like properly. But in this case, we are actually going to make use of this type of division. And also, uh, we are going to divide in that error part, actually this division error part, we might not have to handle here in this case. We might, if we specify a number which is will not specify this number directly, we'll be always storing the number in the register first and then we'll be dividing it, so that way we can avoid the division error. My point is that right now you can ignore the concept of division error. You just can concentrate on these other parts. Like if we are going to perform a 16-bit by 16-bit division operation, the result of this, the quotient part is going to store in AX and the remainder part is going to store in DX. That's our point of interest. Now, once we have learned this, now let me show you, since this division instruction I have not showed you before. Let me show you it by writing a program, and then we'll be making use of these concepts to strip those digits separately. Okay, so for that reason, let me write this program. So for example, we have a number. We have this number, which is a word, and say the number is 1, 2, 3, 4. What we want to do is we want to divide this number by 10. So for that reason, first we have to copy that number to AX register, and then we will be copying, say we'll be using another register, say for example CX, and there you can use any register. Here I'm using CX. Okay, CX to 10. By this CX we will be dividing these AX actually. So for that, how we can do that? Div CX. If you write simply div CX, what it will do is it will divide AX by CX, and the result will go to Q. I mean, Q will go to AX and R will go to DX. Next time again, if we perform this same instruction, div CX, what will happen? It will divide the content of AX by again the by cx. Now see, this div will change the content of dx, content of ax actually. For this div, ax was 1, 2, 3, 4. For this div instruction, ax will be 1, 2, 3. You should realize that. Okay, I'll be showing you the output. I'll be showing you. I'll be executing this program in debug mode, and I'll be showing you. That way, you will come to know what I mean. But before that, let me tell you one more thing. That the thing is, every time you perform this division instruction, one thing you have to make sure is that you clear the dx register. How do you do that? Just by writing. There are ways of clearing it. One way, simplest way, is that you perform XOR of this dx register with itself. When you perform XOR of a number with itself, the output is 0. Okay, so it means we are clearing the content of this XOR. Dx comma dx will perform the XOR operation, and the result will be stored back in dx. So that way the content of dx will be clear. Why is it so? Say, for example, you have a bit pattern 1 0 1 1 0 1. This is certainly a number. Again, if you perform XOR with it 1 0 1 1 0 1, what will be the result? 1 and 1, both of them are same, so the output will be 0. 0 and 0 same, so output 0. 1 1 same, 0. 1 1 same, 0. 0 0 same, 0. 1 1 same, 0. So result will be, so if you perform XOR with the same thing, then obviously the result is 0. So that way we are clearing. Every time, you have to remember this, every time you're performing this div instruction, you have to actually first clear this dx register. Okay, now let's execute this program in debug mode and see what values goes to AX register, what values goes to DX register after each of these div instructions. That will give us some idea about this, how this div instruction is working. And once we know that, then we'll be making use of these repeatedly performing this integer division and remainder operation till we get a 0 to separate these digits from the number. I guess this concept you got. Now this is the time to actually write the actual code. So first we'll be making sure about this div instruction, then we'll be moving forward to write the logic of this program. Okay, first let me execute the program in debug mode, and let me show you the division instruction in work so that you get the idea first. So I'll be writing tasm. What is my program number? pp12. Okay, tasm pp12.asm, and then t-link pp12, and then pp. But I want to show you the output in debug mode. So td pp12. Done. Okay. Done. Now let's execute ds to ax. ds will be same as ax for 8ae. And then move cx comma 0, move ax comma 0008. 0008 within square bracket means the memory location within ds register, within data segment, not ds register, within data segment, whatever it is there at the byte number 0008, from that position 2 bytes, conjugative bytes, will be copied to ax register. First let me show you what is the content of this data segment. Now in data segment 0008 byte, at that point D2 is there, and 0009 byte is 04. So these two consecutive bytes will be copied as the content of these AX register. It means here what will go? See, the lower byte is D2, so it will go to AL register. So this part will become D2, and upper byte is 04, so this part will become 04. So as soon as I press F7, you will see 04D2 as the value of this AX register. 04D2. Let me press F7 at the count of 3. 1, 2, 3. 04D2. Okay. Then we're copying A to CX register. 10 to CX register. So CX will become 10. And then div CX. It means we're dividing AX by CX. Now here, see, we copied actually in our program. In our program, we wrote dw as, when we copied number to ax, number was 1 2 3 4, but it is now here 4 8 d2. That is actually the hexadecimal equivalent of 1 2 3 4. Let's confirm it just by using this calculator. Decimal is 1 2 3 4. hexadecimal we want to know 4D2. That's the, and that's what it is getting stored here, right? 4D2. So we are actually dividing, when we write div cx, we are dividing 1, 2, 3, 4 by 10. And when we perform 1, 2, 3, 4 by 10, we know the quotient is going to be there in ax, and the remainder is going to go there in dx. So what will be the remainder? If we perform 1, 2, 3, 4 by 10, remainder will be 4. So dx will certainly be 4. But what will be this ax? What will be the quotient? 123. And equivalent 123 in decimal, I mean, decimal 123 is actually 7b in hexadecimal. So you will be seeing a 7b here once I press F7. I mean, XOR dx will clear it, certainly. It will not change this. But this div instruction actually. Div cx will make this 7b, which is 123, and this dx to 4. dx4, it is 7b, right? And again, we are clearing XOR dx. This dx will become 0 again. Div cx. Now we are performing 7b by cx. Cx is still 10. 7b means 123 by 10. 123 by 10 means quotient will be 12, which is ABC. So in A, after this div, AX will be C, and 123 mod 10 is 3, so DX will be 3. So this will become C, this will become 3. C and 3. C and 3. Got it? So that's how this division works actually. So what we know is if we are performing 16-bit by 16-bit division, point of interest is that the quotient will go to AX register and the remainder will go to the X register. And remainder is actually the the digit which is being separated from the number. That is the digit that we want to display actually. And you see here, since we are performing the division operation by 10, whatever the remainder it is, it will always be less than 10. It means it will always occupy, the remainder will always fit in this DL part of this DX register. It means we can actually directly send this DL to output screen if we want, just by storing 2 to AH and calling int21h. Got the point? Up to this point, things should be clear to you. Now we are ready, since we have understood this div instruction, now we are ready to write, like to separate those digits. I mean, to write the logic that will actually separate those, digits from the given number. Okay, we don't need two div instruction here. We'll be using certainly a loop. Let me show you how we can write the loop. The first thing is we'll be copying the number to AX. That will be done once. Copying the the divisor to CX. That will also be done once. And then first thing that we'd like to do is we'll check if the we'll be comparing the number, whatever it is there in AX, with 0. Okay, now if the number is 0, we'll be saying, okay, this is the end of the program, so you just terminate. So jump to terminate, say terminate. Okay, that is, here I have this part of the code that terminates the program. So if we reach 0, then it is terminated. Otherwise, what we want to do, first thing that we want to do is we want to perform this division instruction, or that is already written. I don't have to. So we want to perform this division instruction. But again, just before performing division, every time we have to clear dx. So we are writing this dx, clearing dx, and then performing the division. And once we perform this division, then what we have to do is we got our character, interested character, in the L register in some way. May not be the exact value is there, but the digit is somehow there in DL register. We want to display those digits, right? So let's display those digits as it is actually, without doing this conversion. Where here? We want to display digit 9. Basically, we have to actually add 48 to that 9. Then only we'll get the actual ASCII code. But without adding 48, let's display those characters as it is. We might see some garbage characters, but then also we'll get some output. Let's see, and we'll build from that point onwards. Okay. Now div cx is okay. It is going to perform the division, and the quotient is going to go in AX, and the remainder is going to go in DL. I mean DX, but here you can safely say that it will go to DL register. Now we want to do what? We want to actually display the content of DL on the screen. How do you do that? Yeah, we do not have to copy anything to DL. Already it is there. So now next thing is we have to copy to AH register this 0 to H, and then we want to display. So I'll be calling int. We'll be executing int21H instruction that will call the appropriate interrupt service routine to display the character on the screen, whatever it is there in DL. Done. And once it is done, after that, once that character is say displayed on the screen, after that we want to go back to to this point. See, we do not have to change the value of AX explicitly by ourselves. This division will automatically change the content of this AX register. You got it? Yes. So we want to go back to here. So let me call it say L1. And after displaying the character, say we want to go back to L1. So I'll be writing jump to L1. When the process will stop, then whenever this AX becomes 0, and every time we are performing this division, this AX value, every time we are actually dividing it by 10, this AX will go down, down and down and down, and at some point of time it will become 0 certainly. If now I execute this program, everything is fine, but there is certainly a mistake here. I mean, something that we did here, see here, the inconsistency is there in this program. Why? We are expecting that the number is there in AX, and we have to store the number in AX because we are performing this division instruction. We are executing this division. But here, when we display the character on the screen, we have to display this character on the screen. That time we are explicitly modifying the content of AH register. So as soon as we change the content of this AH register, it's a very high probability that the actual value which was there in AX, it got changed. Yeah, the value of AX is allowed to be changed, but only by this div instruction, not by some other means. But here we are explicitly doing it actually. Why we're doing it? Because we wanted to show the result or the content of DL on the screen. So for that reason, we have to write these two lines. It means we are sort of trying to modify the content of AX here, which we are not supposed to do, because in the next iteration then AX will be something which is sort of modified. I mean, not the AX that it should have received, right? So for that reason, what we can do is to overcome that problem. Since we are actually explicitly modifying the content of AH here, first thing that we can remember is AX in some other register, and then once we perform this instructions, then we can restore the value. How do we do that? Say for example, move to this BX is not used, so I'm using BX register. To BX register, I'll be copying the content of AX before actually changing the value of this AH register, and then change it, display it, and after displaying, again we'll be storing back move to AX register, whatever it is the content of BX register. So that way our problem will be solved. And after that, again, you jump to L1, it will compare. If it is 0, then terminate. Otherwise, display the character as it is on the screen. Not as it is, display the character. Yeah, that's now our program is at least, I guess if I execute this program, we'll be getting some output, although we might not get the exact output that we are expecting, but still we'll get some output. Let's see what is that some output that we get. And from that point, we'll try to, build. So for that, let me first terminate this program. Okay, and then file quit. I recompile, I relinked, and I re-execute. This time I'll be executing the program directly. TP12. We are getting the output as blank. Why is it blank? AX is number. Did I copy the number? AX is the number. CX is 10. Yeah. Compare AX with 0. If here I'm writing jump terminate. Okay. How can I do that mistake? Jump on equal terminate, and then things will be done. Just let me know how many of you have actually noticed the error before when I did it for the first time. Let me know it in the comment section. I just want to see. Yeah, we got some output, and this output is right in one sense at least, if it is not completely right. And in what sense it is right? It is showing you 4 different symbols. In that sense, it is right. Why? Because in our actual number, there are 4 digits. Let me say, for example, we want to display 64,000. That is within the range of 16 bits capacity, right? So 64,000, how many digits are there? 1, 2, 3, 4, 5. So we should be able to see 5 different symbols on the screen as an output, at least for the time being. 5 different symbols are done, but again, those 0000, that is, null is coming, so that's why it is like that. Okay, let me try it one more time. Not 64,000 this time. Say, for example, 1, 2, 3, 4, 5. It is certainly less than 64,000 something, so it should display you 5 different characters on the screen. That's what I want. 5 different characters on the screen. Yeah, we got it. The only thing is that those characters are not the characters equivalent to. I mean, those are not the digits character. Those are some sort of garbage characters, right? Although not garbage. Where is the problem? As you know, we are displaying the content of DL as it is on the screen. Where we are displaying the content of DL here. This point here. This line for remembering, this line for restoring, and this line for displaying the content of DL. And from where we are getting the content of DL, this division is actually, it is simultaneously updating the content of AX, and also it is updating the content of DX. It means indirectly it is updating the content of DL. Now, that DL we are displaying directly, but directly if we display, we are going to get those, those different characters. But what we want those corresponding digits, and we already have seen how we can convert those digits. I mean, in DL, what are the values? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. On out of these, any values could be there. Those values, if we want to convert to corresponding ASCII characters, we have to add 48 to those values, isn't it? We have already seen that. So we'll be now applying that concept here, and we'll be adding to the DL register, whatever it is the content of DL, to it we'll be adding 48 decimal or 38 in hexadecimal. So once we do that and execute this program, you see, you're going to get the right output, sort of. Not completely right. Why not completely right? Why you cannot say completely right? Because see, 1, 2, 3, 4, 5, yeah, it is displaying you the digits, but in reverse order, isn't it? See, however, the point is, this is 5, 4, 3, 2, 1. It's not a single thing now. It's just those digits are displayed one after another. But since they are displayed like just one after another, we are seeing them as a sort of the number is reversed and then displayed. But what we can do is, just to show you that those digits are displayed separately, what I'll be doing is, after displaying this DL content on the screen, modified DL content on the screen, I'll be displaying maybe a new line or a space. I'd like this space. So to DL register, I'll be copying this space, and then after displaying the digit, I'll also display the space. Okay, so that way it will give some space after each digit. 5, 4, 3, 2, 1. Right? Now we know how to split those digits separately and then display them. But still, the problem is not completely solved, because our output is 5, 4, 3, 2, 1, not 1, 2, 3, 4, 5. We want 1, 2, 3, 4, 5, not 5, 4, 3, 2, 1. Now, if you see here at this, what we're doing here is we are extracting this div is actually giving you the last digit in DL register, and then we're displaying the content of DL register in some way, right? But this approach itself extracts the digits in reverse order, and so at the same time, if we display, certainly you're going to get the output in reverse order. So if we do not want the output in reverse order, then what we have to do is, there are different ways are there, like sophisticated ways are there, like you can use a stack. But since we have not talked anything about stack, so we'll not be using it. We'll be using something that we already know, and that something is string. So what we're going to do is, we are not going to display the digit as soon as it is extracted. Instead, what we'll do is, that digit we are going to put in a string, and at once all the digits are extracted, then we'll be displaying the string. If the digits are there in a string, then we can reverse the string by writing simple code, and then we can display the reversed version of the string. What I said, it might not be clear, but up to this point things are clear. If it is not, just pause the video. uh, and again, I always encourage you people to write the code by yourself and see. Just type this code, pause the video, type this code by yourself and see the output, and then think whether all these different lines makes sense to you, whether you understand the concept or not, and then again proceed further. Okay, now up to this point we have solved. Now our problem is, now we'll be concentrating on how we can get the output in right order. And for that reason, we will, as I said, now we are not going to display the character immediately. Rather, we are going to build a string first, and then we are, once we have that string, then reversing it is not going to be a very big job. Okay. Okay. First, let's see how we can construct this string. Okay, so for that reason, first thing is, let's create a blank screen, a blank string. How we can create a blank string? Okay, string one of bytes. How many, like still now, whatever the strings we wanted, we immediately stored, like hello world if we want, then we can store it in this way, hello world with a dollar symbol, because we know the content of the string. But here we do not know the content of the string. So if you create the string in this way, you can think, okay, it is a blank string, but the thing is that this string has only one character. In this string, you cannot store any other thing, right? But we want to store. So we want a blank string in the sense that we need a string where all the characters are sort of dollar, means the first character itself, the end of the string. But logically, if you think, there's spaces there. If you want, you can change those content. Initial content is dollar 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 dollar. At this point, if you want to display this string, certainly it will not display anything on the screen, because the first character itself marks the end of the string. Okay, so that's how we want to start. Now, how many characters we might want in the string? Say the maximum number that you can represent using 16 bits will be around 65,000. So 65,000 means 651,000. So 1 2 3 4 5 characters plus the end of this string, so 6 characters will be enough. So 1 2 3 4 5 6 characters. This is how you can display, you can create a blank string sort of. Now there is a shortcut also. Suppose the same thing you can achieve in this way also. Say for example, string 2, it is a bytes of array, and you need 6 characters. You can write it in this way, and all those 6 characters should be this dollar symbol. So you can write in this way. Both these two lines will be doing the same thing. Here also you are creating an array of $6. Here also you're creating an array of $6. See, you're creating first a string 2. It's an array of 6 bytes, 6 bytes, and then each of those bytes will be this dollar symbol. Anyone, if you want, you can take, but let me take this more the simplest one, which explains everything in itself. But certainly, if you want, you can use that DUP directive. Okay. Now the thing is, yeah, okay, and yes, we have this blank string, and now the next point is how to build the string. I mean, how to put content in the string, right? What we have done here is, you just let me give you, quickly go through it. Okay, my internet is gone or what? Okay, when you write this in any way, str1, you can do it in this way or that way. Say 6 characters of this dollar symbol, or string 1 db, and then dollar 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 dollar. This, both of them is going to, both these ways, you will get a, in the data segment somewhere, you will get a string where all these characters are dollar 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 6336 65,000 and dollar. Okay, now this string will be stored something like this, in this fashion. in the memory, like each byte will be stored consecutively one after another, and the content of each byte will be this dollar symbol. Done. Now what we can do is we can make a register. Make a register means a base register we have to use, or we can use this bx register actually. So he here this byte number, say suppose for example this byte number is, say for example 900 in decimal, so this will be byte number 901, 902, 903, like that. We want this 900 to be stored in bx register. How do you do that? We can use lea bx comma of the string str1. So that way this bx will have this 900. This we already have done, right? So we know how to copy the starting address of a string to a particular register. Done. And also we can use like si, this source index, to be initialized with 0. Now what we do is every time we get this symbol, see, when we write these lines here, just show me the program. When we perform this division operation, where this division operation, we got our result in DL, and then we can convert it to a the appropriate ASCII code, and then that character in now after that we displayed the character. But here what we want is we do not want to display the character. Instead of displaying the character, what we want to put it in the string. How you can put it in the string? You can actually put it in the string in this way. Say whatever it is the content of bx plus si. This is a memory location, like bx plus si means whatever it is the content of means whatever it is the value of bx plus whatever it is the value of si, add them up, whatever the memory location it represents. In that memory location you want to put the value of this dl register. Okay, so here up to this point it will be fine, like div by cx and then add 48 to DL register. Done. Now DL, whatever it is this DL after this add operation, instead of displaying it on the screen, what we do is we put it to the string here like this. So if it is the first digit, I mean the last digit, say for example 1 2 3 4, if this DL is in the first iteration, then it will take out this 4, and that 4 will occupy this first position. And then certainly in our code we have to increase the value of si, so that in the next iteration it becomes 1. So that way whatever the character we extract in the next iteration here, that will be 3, that will go to the bx plus 1. If bx is 900, bx plus 1 will be 901. So that 3 will come to this. Similarly, now you can extrapolate. This 2 will come to this, 1 will come to this particular character, and then rest of them will be dollar and dollar. Now see, if I display this string, it will display from beginning to till it encounters this dollar symbol. Okay, got it? If you have understood this point, then we are ready to write the code then. Okay, at this point we want to store the character on the string. Here we are displaying it, but we do not want to display it now. We want to store it on the string. Now how do you do that? Now see, why did I write move bx comma ax? Oh, we wanted to remember. Now this remembering, see, remembering was important if we had to display the character on the screen, because if we have to display it, then it means we have to modify the content of ah. But if we do not write these two lines, we are not modifying the content of ah. It means we do not have to remember it. I mean ax will remain intact. So let me get rid of these lines here. This we do not need. Then certainly we do not need to display them, like this displaying thing is not needed anymore here. Okay, so if we remove, then our content is something like this right now. Compare with 0. If it is equal, then terminate. Let it be terminate for the time being. Then clear dx, perform this division, add, update the prepare the content of dl register by adding 48 to it, and then here we have to actually move this dl to the string. How do you do that? We only have this declared the string. Now next thing that we have to do is we have to load the effective address of the string to the bx register. LEA to bx register the effective address of string 1. That will make this bx to point to the starting of the string. That is the first thing. And the second thing that we want is we want to store these si initially the value of SI to be 0. Okay, it is SI will be using to move from one position to another position in the string. Certainly, we could have increased this BX only, but yeah, I prefer for some reason this SI part. Okay, done. Now, if it is our initial setup is done, then what we'll be doing is then copying this number and copying this divisor is done once at the beginning, and then we'll be comparing it. If it is 0, then let's say it is terminated. Otherwise, clear, add it, and then here we have to move the DL, the content of DL, to which register? Not register, now to memory location. Whatever it is, the BX register, value of BX register plus the value of SI, add them up, whatever the memory location it points to. In that memory location, we want to copy this DL register, the content of DL. Done. And once it is done, we also have to increase these SI so that next iteration it points to the next character or the next location. Done. And after that, what else? Then move AX comma BX. It is not needed anymore, certainly, because we are not using it. Yeah. And then jump L1, it will go back to this point, and this process will be repeated. Now let's just mentally check this program. Base address or the starting address is loaded to BX, SI 0, copy the number, copy B10 to CX, done. Compare until and unless it is 0. If it is 0, then this is not terminate anymore. Then display results, say display result. Okay, and we have to write certainly the code for this display result. We'll be writing it in a moment. And it means if AX becomes 0, we are ready to display the results. Otherwise, what we have to do is first clear DX, perform division so that AX contains all the digits except the last one, and DX contains or DL contains the last digit. So we convert the last digit to its equivalent ASCII code by adding 48 to it, and then whatever it is the character or the ASCII code that is in DL, so that we are copying it to the memory location pointed by BX plus SI. For the first iteration, SI is 0, BX is the starting address, so it will go to the first place of the string. And then we are increasing SI so that in the next for the next iteration it will be pointing to the next character. Jump L1. Again, it will go back here. Again, it will check if it is 0 or not. If it is 0, it will display it. We'll see what is that, what should be the code of that part. But if it is not 0, then again it will repeat. It will go for the second and the third and the fourth, and like that. All the digits will be extracted one by one in reverse order. That. Now what is this display result then? RESULT. Sorry, this display result. In that case, we just have to display the content of the string 1 on the screen, isn't it? So just display it then. Load the effective address of the string to DX register, and then store AH 09H in AH, and then display it. And after that, terminate. By default, it will be terminated. Okay, then that's our program. If we should get the output here, but again, it will be in reverse order. But if we get this output here, then solving the problem of this reverse order will be very straightforward. Okay, let's compile and execute this program and check the output. Compile, no error, no warning, then linking, okay, and then executing. 54321, and this is the string actually. This 54321 is actually the string. 1 2 3 4 5 was the number. 54321 is the reverse string representation of the given number. Let me write here a number, say for example 7865. Okay, 7865. So it will be displaying as the output as 5687. 5687. Okay, we are very much close now. Only thing that is left is somehow we have to okay, let me show you what if I store the number as 0. That I'll leave as a homework actually. I mean, exercise. If I leave the number as 0, then the string will be blank actually. It will not work for 0, as you know, because this, when you compare, suppose the number itself is 0, so you copy the number to here, you copy the number to ax, then you do this certainly. But here, when you compare ax with 0, it will be 0 equal, it will jump the, it will transfer the control to display register, I mean display result. Here it will display the content of the string. So the content of the string will be not changed because this part has never been executed. It means the content of the string will remain this. It means a blank string will be displayed. So if I give the input as 0, certainly it is not going to give it output. That is one place where it is not going to work, certainly. If I compile, link, and execute, see, it will not display you anything. That's one point. If I store the number as 10 or 100, will it be displaying me what it will display me actually? Yeah, it will display 1001. I mean, that will be right, I guess. 001. Okay, that's I mean in the reverse order also only, but anyhow, if it is, if you give 0, certainly it is not going to display you anything. Other than that, any valid unsigned integer number, if you write here within the limit of 16 bits, then certainly it will display you. At least the reverse we are getting right now, right? Now here, let's forget about the, like, we'll try to solve this 0 problem at the end, but let's suppose for other numbers, this display result should actually, not display the string as it is. Instead, it should display the string in reverse order, isn't it? So for that, we can do actually one thing. We can read the string in reverse order and then display, or we can actually convert, we can actually interchange. Reversing the string itself is a different program, isn't it? So here, let me display the string in reverse order, and that will solve our problem. Okay, display result means we will be displaying the content of the string in reverse order. Okay, but here, since we have used this si, at this point we know, like, the si is going to be the number of characters present in the string. See, in the first iteration, see, every time if si is 0, it means there are like 0 numbers of character. But once we store a character here, we are increasing it. If si is 1, it means there is 1 character. If si is 2, it means there are 2 characters. You see here, initially si will be 0. When si is 0, there are no characters. But once we store the first character, immediately we increase the si, so that si will be pointing to this. It means si has 1, I mean the string has 1 character. So whatever it is the si after the execution of the loop, uh, that many characters will be there in the string. That thing should be clear to you. Okay, that is, it means si is actually nothing but the length of the string. So if you know the length of the string, then printing it in reverse order, do you think it's difficult? I don't think so. Let me do it. Okay, how do you do it? Just think and you'll come to know. Right now, bx is, we can make this bx to point to the beginning, si is pointing to this. Yes, okay, we just have to get down this si to 0, that's all, isn't it? Mhm. So we can start from si minus 1 till 0, right? So we can do it in this way. But we have to display the content of the string one character at a time, okay? So let's start with this. Decrement si. Is it the case? Whatever it is the value of si, that many times we want to execute the loop. It is as simple as that. And the first character will be, see here, where will be the first character? Okay, say for example, the number was 1, 2, 3, 4, 5. And after doing all these iteration and all, this string one will have these characters 1, 2, 3, not 1, 2, 3, 4, 5. Had it been like this, we wouldn't have, writing this program. 5, 4, 3, 2, 1, and then obviously this is null, and then our SI will be pointing to this point at the end, right? And our BX will be pointing to this first memory location. Yeah. So if we want to print this string in reverse order, then first we have to print, say we decrease the value of SI by 1, SI minus minus, so that it points to, yeah, we decrease SI. Okay, we can do it in this way. Decrease SI and then print BX plus SI. Okay, and then loop or repeat. Where first thing is we have to see, like, if SI is 0, okay, so we'll be comparing. Compare SI with 0, jump on equal, terminate. Otherwise, decrease SI, print the character, and repeat. Repeat means this. Again, compare SI with 0. If it is not 0, yeah. If it is not 0, I mean, yeah, if it is 0, then terminate. If it is not 0, decrease it and print the character and repeat. So this will print the string in reverse order, I guess, right? Okay, let's do it here. First, we'll be comparing C, what was that? SI, no? SI with 0. And then if they are equal, then terminate. If they're not equal, then we would like to print the character on the screen. By first, we'll be decreasing it. So decrement the value of SI. Okay, and then copy the content of the BX register. BX is still pointing to, we have never changed the content of BX after we loaded the starting address at BX, right? So still we can use this BX plus whatever it is the value of SI. That content we have to copy to DL register so that we can display it actually. And after that, we have to display using AH register. We have to do it again. So we have to copy to AH register 0 to H and then int 21H. And after that, this tree is not needed. And after that, we want to repeat repeat. Repeat, did I use before any? No. So if it is not, then repeat, or let me call it jump to L2. Okay, and this part here, comparing this thing L2. I'll first compare SI with 0. If it is 0, then done. Otherwise, decrease it and copy the character and display it and done. So that way it will display the string in reverse order. First we constructed the string, then we displayed the string in reverse order. If this works, then our problem is almost solved. 100. Did we store 100 there? 100, yeah. Now 1, 2, 3, 4, say. If it is the string, then our output will be 1. It should be 1, 2, 3, 4. 1, 2, 3, 4. Yes, that's how. See here, whatever it is the content of AX, I mean D, whatever it is the content of that particular word, those 16 bits, those are actually displayed on the screen as its value. Say for example, I said if 97 is stored, then 97 should come as the output, right? So 97 will come as the output. Yeah. I said 65 H, if it is stored, equivalent is still 97, so 97 will again be coming as an output. Recompiling it, relinking it, re-executing it. 65H is 101, I guess. Okay, 61H, what is that? I wrote, did I write the wrong thing in my first screen? 61H I said. Let's see whether 61H is 97 or not. Okay, I just wish it is true. I mean, sometimes I do mistakes. 97. Okay. Otherwise, I would have again, to retake the video. I mean, like this is most probably 3 or 4 times I recorded the video. I mean, somewhere I do mistakes, and again I have to start from the beginning because I don't like editing much. So what I do is I try to record the entire session in just one go without retaking, and I just try to avoid editing. For that reason, sometimes what I have to do is after recording, say 40 minutes, 30 minutes, even 1 hour, I find mistakes there, and I have to re-record the entire session. But anyhow, I mean, I said it. So you got the output, right? I mean, that is what we wanted. Anything else? Yeah, anything else? A small problem is there still. I mean, if it is zero, then how do I solve the problem? If it is zero, I mean, say for example here, where is the number? Here. If it is zero, then how do I solve? If it is zero, it is not going to give us any output. See? No output. Yeah. So what I want you people to do is you people try like what modification. You just have to do some small modification here. What modification will you do to this program to take care of that zero condition also? Like if the value is zero, the output should come as zero. You just have to write somewhere a slight modification. You compare. I will not tell you. I mean, okay, let's try to solve it. You people try to do it by yourself and let me know it in the comment section. What will be the solution? How will you fix this problem here? Like if the given number is zero, right now this particular program is not giving you output. What modification will you do to this program to give you the output? I mean, even if if you write zero, the output should come as zero. Now see here in this program, I mean, certainly there are, as I said, no, there are some other ways also solve the same problem. Say, for example, you can use a stack. If you're using a stack, basically, you do not have to do this reverse thing explicitly by yourself. Okay. This stack is very much suitable for such operations. So we can use this stack, but since I never said you anything about this stack, so I kept it for my future videos. I just wanted to solve this problem based on the concepts or based on the things that we already know. So my point is, you go through this, you try this program by yourself, write this program by yourself, and at the end try to solve this problem. Like instead of if I write the number zero here, the output should come as zero. What modification will you do to this program to get this output? Okay guys, then that's what I wanted to tell you in this part of the video. And this video I was like, I have been saying that I had been saying that I will be doing a and I'll be writing the program for doing this task, and ultimately I did it here. And why did I like postponed this program so long? Because see here, all these different concepts we actually initially needed to know, like the addressing modes, or iterating over the content of an array, and all these stuffs we first needed to know, and that's why I postponed this video up to this point. But I guess now you people have understood, and you people will be able to write the program by yourself after seeing this video. Okay guys, then this much only in this video. See you guys with some new content in the next part. Till then, have a nice day.